Okay, so now we're going to start some of the named distributions that we have formulas for. And the first one we're going to talk about is the binomial distribution. And shape of u, that's funny because the shape of the binomial distribution, the shape of the histogram kind of depends on what the probability is. But that's just a little preview of things we're going to talk about. Okay, so in this first one, I want to talk about what a Bernoulli trial is first. So a Bernoulli trial is an experiment that has these three factors. Each trial, this will say has, not was, typo, has only two possible outcomes, true or false, yes or no, success or failure, heads or tails, one of those, okay? There's only two possible outcomes, okay? That's really, really important that you have that because otherwise we're not Bernoulli. Each trial is independent or nearly independent. So nearly independent meaning that, of course, if we are sampling from a large population without replacement, we can still call it independent because the probabilities don't change very much. And the probability of a success P remains constant in each trial. So that means that each time we do another trial, and a trial is just a little experiment, like selecting someone at random from the United States, or rolling a die, or whatever it is, flipping coins, choosing someone that's an undergraduate or graduate, a win or a loss, anything, okay? A success and a failure. Doesn't always have to be. Success isn't always a good thing, because sometimes it can mean that somebody has some horrible disease. So Bernoulli distribution, if a success is 1 and a failure is 0, the probability of a success is, of course, well, it can only be 1 or 0. So the probability of a failure is going to be, depends on what the probability of a success is. So if, let's say the probability of success is 1/3, and the probability of failure is then 2/3. So the probability of a failure 0 is going to be 1/3 to the 0 power times 2/3 to the 1 minus 0 power, or 1 power, and anything to the 0 power is 1, so this makes this 2/3. And the probability of 1 is then 1/3 to the 1, 2/3 then to 1 minus 1, which is 0. It makes it 1/3. Now this seems kind of trivial to do it this way. So if p equals 0.7, then we have it this way. And then we have a histogram that looks like this, which is kind of silly. And the mean is just 0.7. The mean is just p, okay? And the standard deviation is the square root of p times 1 minus p. So that seems a little bit trivial. So let's bring it on to the binomial distribution. Now the binomial distribution, you have n Bernoulli trials. Okay, so we're going to flip a coin n times. We're going to select n people from a large population. We're going to check and see if we run over a cone or not n times. Anything like this we can do, okay? So we're going to try n times and see if on slick roads, and we're going to put a cone, and we're going to see if we hit the cone or not. With different cars, maybe. Something like that. We can do all kinds of things. So the random variable x counts the number of probability p successes. So how many yeses do we have? So let's look at this. Let's look at the number of people out of 3 who have a smartphone. Now, 80% of the population approximately has a smartphone. We can easily list these probabilities, right? So we're looking at what's the probability that none of these people have a smartphone. Nobody has a smartphone out of 3 people. Well, that's just going to be, it's independent, so 0.2 times 0.2 times 0.2, which is 0.008. So that's pretty small, okay? However, what's the probability that one of these people? Well, 0.8 times 0.2 times 0.2, but remember, this person can be second or third, so that's times 3. So what's that going to be? 0.16.32. 0.8 times 0.2. Whoops, didn't get my point on there again. Always that first one. Times 0.2 times, oops, times 3, okay, 0.096. I already had the 0. Ah! 0, stop. Okay. So then, 2 people with smartphones, 0.8 times 0.8 times 0.2. And again, this 0.2 can be first, second, or third, so there's 3 ways to do that one. So let's see what that one is. 0.8 times 0.8 times 0.2 times 3. 0.384. And for 3 of them, 0.8 times 0.8 times 0.8. There's no different way to do that. So that's just 0.8. I'm going to do this easy. 0.8 cubed, 0.512. Okay, so these are all the possibilities. So 0, none of the people we choose at random have a smartphone. That has a 0.8% chance of happening. Only one of them having a smartphone only has 9% chance of happening. 2 of them having a smartphone is 38%, and all of them having smartphones is 51.2%. This is if we do this truly randomly, of course. Certain populations are much more likely to have smartphones than others. So let's look at this for a minute, and let's think about what we've done here. So here we've done 0.2 cubed. Here we've done 0.8 to the 1, 0.2 squared times 3. Here we've done 0.8 squared times 0.2 to the 1 times 3. And here we've done 0.8 cubed. Interesting. So you notice a correlation between this, and I could also say we have 0.8 to the 0 here and 0.2 here to the 0. So if you notice, there's a correlation between this and this in the binomial distribution. And we'll notice too that these two always add up to 3. The 2 exponents always add up to 3. And that is interesting. Okay, so that is kind of a preview of how we're going to do this. Now, before I really get into how to do the binomial distribution, I want to talk a little bit about some background review. I want to review with you factorials and combinations. So a factorial is denoted by n, boom, whatever, bam, seems like it, wow, whatever, an exclamation point. So we have 1 times 2 times blah, 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 times n minus 1 times n. We have 0 factorial. Since it's kind of weird, it's just defined as 1. Don't ask too many questions about that. That's just what made it all work. Okay, so 0 factorial is just defined as 1. Everything else, you just take all of the numbers before it, all of the counting numbers before it, and multiply them together. So 4 factorial, 1 times 2 times 3 times 4. 5 factorial, we multiply it by 5. It would be 120. 6 factorial would be 720. 7 factorial, I don't have that one memorized, so we're not doing it. Okay, so combination or choose notation. So sometimes you might have seen this look like this, possibly. I might have done that a few times in here. I think I've changed them all. But your calculator actually uses this setup. So we're going to be using this setup. And it's defined as n factorial divided by x factorial over n minus x factorial. And combinations are the number of ways that in this case, X can be arranged, I should say X items. X items can be chosen from N items if order doesn't matter. Okay, for example, if I have a committee of, say, 5 people, I have a committee of 5 people, and I want to know how many ways can I choose 2 out of this. So here's person number 1, 2, 3, 4, and 5. Actually, not to be confusing, I'm going to call these A, B, C, D, and E. So how many groups of 2 can I get out of this? How many groups of 2? So I can have A, B, A, C, A, D, A, E, B, C, B, D, B, E, C, D, C, E, and D, E. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can have 10 groups of 2 out of this, out of a set of 5. So that's 10. That means that 5 choose 2 equals 10. And order doesn't matter. See, A, B, and BA is the same thing. Doesn't matter. These 2 got chosen. So to do this, we're going to go 5 factorial over x factorial, 2 factorial, and then n minus x, 5 minus 2, 3 factorial. So what we have is 120 over 2 times 6. So 120 divided by 12 is 10. We can easily figure that out. Another way to do it, here's 5 choose 1. 5 factorial over 1 factorial. Because if you think choosing 1, well, there's exactly 5 ways, right? 1, 2, 3, 4, 5. There's 5 groups. There's your groups. Over 4 factorial. Well, 1 times 2 times 3 times 4 cancels out with this one. And I'm just left with 5 over 1. And in fact, anything choose 1 is itself, which makes sense. If I have a group of 5, if I have a group of 20, and I want to choose a group of 1 from that 20, well, there's going to be 20 ways to do that, right? And a few more things. There's a few more down here that are pretty simple too. So on your calculators, they're kind of in a sneaky place. So let's say we want to find factorial and combinations. So those can both be found under probability, under math, and then PRB. So for factorials, let's find something we want to find the factorial of. Say 5. So we want to say 5 factorial. It's 120, but that's okay. So I put the number in first. Then I'm going to go math, PRB, so it's this last one right here. PRB, enter. Whoops. I hit enter too soon. Ignore me. 5, math, PRB. Then I go down to number 4. I can either scroll down the number 4, or you can actually hit 4, and it comes up. So, and then you hit enter. 120. There you go. Done. So, for combinations, we want to, let's say we want to do combination 6, choose 3. So I'm going to start, I put in 6 first, 6. Then I go math, go over to PRB again. Now I'm going to go down to NCR, or you could just hit 3, enter. Then, oh, I was doing 2, sorry. 6 choose 2, not 6 choose 3. And then I'm going to hit the bottom number, 2, and then I hit enter. And I have 15. So 6 choose 2 is 15. So some of them you don't even need a calculator with. For example, n choose 0 is 1. So 6 choose 0 is 1. Anything choose 0, because there's only one way to pick nothing. You just don't pick anything. So n choose 1 is n. N choose the number right below it is also n. And n choose n, because there's only one way to choose everything, is 1. Okay, so now we can move on. Now we can look at a few more things. So we can find out how to find the binomial probability by hand. This isn't something we're probably going to be doing a lot of because the calculator has a great thing for this, but I do want you guys to know how to do it and to understand how it works. So the first thing we want to make sure all the assumptions met for the binomial. So is it really binomial distributed? Is this binomial? And binomial meets these assumptions. There's n trials, or like a sample. Okay, they're choosing n people. Each trial has only 2 possible outcomes. Okay, yes or no. They have the disease, they don't have the disease. Whatever it is. Trials are independent of each other. Okay, that includes pseudo-independence is fine. And the probability of a success, P, stays the same from trial to trial. So that doesn't change. So the next thing you want to do is you want to figure out what a success is, what you're going to call a success, and what the probability of a success is. So you need to determine what P is. So what is that? And that's the probability of one success in one trial. So how many trials? So that's your n. Figure out what your n is. And now we can plug everything into the binomial formula. And it looks like this. We can guess. We could have guessed this before. So this is going to represent the number of ways to switch around the successes and failures. That's why you need to have the NCX right there. This part right here this is your probability of success to the power of the number of successes. So, 0.8 times 0.8 times 0.8, etc. If you want 3 successes, you need 3 of those multiplied together. This is your probability of failure, 1 minus P, to the number of failures. So if you're going to have 3 successes, so if you're going to have 0.8 cubed, you need 0.2 to have the rest of them. So if we say this is n equals 5, you want 0.2 is the rest of them. So these 2 things have to add up to the number of trials, and you have to have 5 choose 3. And this tells you how these mix around. So where are the 0.2s and the 0.8s? So let's do a quick example. So 38% of Alaskans are undeclared party affiliation. So if we're choosing 5 Alaskans at random, I'm going to assume that the state of Alaska is a fairly decent population. It's what, 700,000 or so now? Then our random variable X is the number of undeclared party voters chosen in our sample. Using the binomial distribution, let's find out all the probabilities associated with this. So we can do this fairly simply. So we're going to use this. So P, let's identify what P is. Do we have a binomial distribution? 38%. That doesn't change from trial to trial because we have a large enough, we're taking it out of all of Alaskans, and equals 5. So the binomial distribution, probability of X, will look like this. We're going to have n choose X, well, n is 5, I can change that to 5. 5 choose X. Now it still doesn't look good. Every time I erase something, it looks worse. 5 choose X times 0.38 to the x power. And what's 1 minus 0.38? 1 minus 0.38 is 0.62 to the 5 minus x power. So we can easily find all of these. So probability that none of them are undeclared is going to be 5 choose 0, 0.38 to the 0 power, 0.62 to the 5th power. Well, 5 choose 0 is 1, 0.38 to the 0 power is 1, so all we're left with is 0.62 to the 5th power, which is 0.0916. So I want you guys to get in the habit in this chapter of going to 4 decimal places for probabilities. What that allows you to do, if you go to 4 decimal places in probabilities, that allows you to go to 2 decimal places if we take it into percentages. So the probability of 1 is 5 choose 1, 0.38 to the 1 power, 0.62 to the 4th power. So we know that anything choose 1 is itself, so 5 times 0.38 times 0.62 to the 4th power, 0.2808. So probability that it's 2, 5 choose 2, is times 0.38 squared, 0.62 cubed. So remember, 5 choose 2, we found that out on the last page, that was 10. 10 times 0.38 squared times 0.62 cubed. Another way to get cubed is you can also go math 3. Also puts a cube on there. 0.3441. Probability that it's 3. 0.38 cubed. 0.62 squared. So 5 choose 3 is also 10 times 0.38 math 3 times 0.64 squared is 0.2248. Probability of 4 is going to be 5 choose 4, 0.38 to the 4th power, 0.62 to the 1st power. So remember, a number, choose the number below it is always just that number. So 5 times 0.38 to the 4th time, oops. Make sure you hit that side arrow after you take your 4th over there. 0.62. Oops, I forgot the times also. 0.62. There we go. 0.0646. Probability of 5. 5 choose 5. 0.38 to the 5th. 0.62 to the 0. This becomes 1. This becomes 1. And all we have is 0.38 to the 5th. 0.0079. So here's all your probabilities associated with that. You could make a probability histogram with this. There's so many things you can do with this information. So there totally needed to be a user way. Ah, look at that. There's all the answers. Okay, so 0.092. Well, see, I broke my own rule. 211. Oh, why is that 211? Did I do a typo on that 3 one? Did I do a typo on the 3 one? Or maybe I did a typo before. That's always a possibility. 10 times 0.38. 0.64 squared. Oh, I did. It's supposed to be 6.2. Let's redo that one. 0.62 squared. There we go. 0.211, 2109. There we go. Fix the typo. All right. 065008. So now we can do all kinds of things. What's the probability that more than 2 voters are undeclared? More than 2. So strictly more than 2 is these 3. So probability x is greater than 2 is 0.211 plus 0.065 plus 0.008. And I can do it this way. So 0.211 plus 0.065 plus 0.008. I can simply just add up the probabilities that I need. So 0.284. The probability that at least one voter, and remember at least is greater than or equal to, is affiliated with the party. And the easiest way to do at least one is 1 minus the probability that nobody is. So that's 1 minus 0.092. And it's 0.908. That's the probability that at least one voter is, oh, that's tricky, is undeclared. That's at least one voter is undeclared. Ooh, that's a tricky question, I just realized. What's the probability that at least one voter is affiliated with a party? That's a totally different question than this. That's the probability that x is less than 5, so that all 5 of them are not. So that's actually 1 minus the probability that x equals 5, or 1 minus 0.008, which is 0.992. So interesting. Very, you have to be very careful reading some of these questions. Okay. So now we can find the mean or expected number of undeclared Alaska voters out of 5. Now we could sit here and we could go and we can multiply all these together. But if 38% of voters are undeclared, then how many would you expect you to be out of 5? 38% of them, right? So my mean should be 0.38 times 5. Or 1.9. And this would be true. It is 1.9. So we can easily find the mu is n times p, or I did it p times n, but it doesn't matter. And the standard deviation of undeclared voters, if we have something that's normally distributed or binomially distributed, this is np times 1 minus p. So this is going to be the square root of 5 times 0.38 times 0.62. So square root 5 times 0.38 times 0.62 is 1.085. Okay, that wasn't too bad, was it? So here's the probability histogram that I promised you guys earlier. And I want you to notice something about that. Do you see a shape in there? There we go. Now we've got the edge here and shape of you. So what is the shape that you see? I see a small skew to the right, because it's very unlikely that we have 5. It's very likely that we have about 2 voters out of 5, well, 1.9, but it's not very likely we have 5. So we have a little bit of skew to the right on this. So this gives us our easy formula for formulae. That's how I spelled it. That's correct. Check it. If all the assumptions are met. So the mean and the standard deviation can be found. This is only if we're a binomial random variable. All the assumptions are met to be binomial. Otherwise, use the calculator or yesterday's formulas, or last time, whenever last. Okay, so now I talked a little bit about the shapes of the histograms. Now you'll notice that that 0.38 was slightly right skewed. Well, look what happens when a 0.25. This is all with n equals 6. Look, 1 and 2 is very, very likely that you're going to get 1 or 2 out of 6 because there's only a 25% chance of success. So having 1 or 2 is a lot more likely than having 5 or 6. 6 was so small it doesn't even show up. So this is right skewed. When p is exactly 0.5, well, it should be right in the center, right? So it should be perfectly symmetric. And when p is high, we should have more successes. So we should get 5 out of 6 of them being success, or 4 out of 6 of them being success. Much less likely to have 0. That's probably very unlikely. If 75% of the population is something, it's highly unlikely you're going to take a random sample of 6 of them and get 0 and have everybody be something different. So that's the way that those work. Usually this does show up on a test. We will do it again with the worksheets that we have in class. So it's really, really important to know that, to kind of be able to picture what's going on with a binomial. So let's talk a little bit about our calculator. So this is our calculator for binomial probabilities, P of k. And I use k instead of x just for clarity. So basically, we just need to do second vars. So let's do one of these that we did. So let's use my undeclared voter example, and let's use p equals 0.38, n equals 5, and let's say we want to make sure and verify when k equals 2. So the probability that exactly 2 of the voters were undeclared. So what we're going to do is you go second vars. You see this DISTR that's right in here where my little wheel of death is? The DISTR, that's what we want to go to. So second vars, and we want to go down to 0, which sometimes it's easier to go up to it. Well, 0 or A. Some of them are 0, some of them are A. Binomial PDF. You want to make sure it's the P, not the C on this one. Hit enter, and then you enter N and P and K. So it's in that order. So number of trials is 5. The probability of a success is 0.38. And the X value we're looking at is 2. Paste these in, hit enter, and you get what you need. You get your 0.344, which I believe is what we got before, correct? Let's make sure. 0.344, that is correct. So we got the same answer. So, and then I also wrote down TI-89 and Inspire. Now, I also said down here, without K, it will give you all of them. So if I wanted to do this and take the normal or the binomial and find them all, I could actually just leave off the X value and will give me a list of all of them. And I can scroll through it this way. It works much better on your calculator than it had. My scrolling to the side doesn't work very well on the simulator that I use. You can scroll to the side and see them all in order 0 to 5. So using the calculator to find less than or equal to probabilities. This is also called at most K. Okay, so K or less. So let's try to find the probability X is less than or equal to 2, with P is 0.38 and N is 5. So in this case, we go back to distributions, but now we want the binomial CDF. You have to be very careful. CDF is The C stands for cumulative, if that helps you remember, because it's everything up to 2, 0, 1, and 2. So binom CDF, number of trials is the same, 0.38, and we're going to put in 2. And of course, this will do the same thing before if you don't put one in. It'll do all of your cumulatives. And this says 0.71 or 716 or 7165. So this is the same as if we went back here and we added all these up, we added these 3 up, that's what we should get, is 0.716. And I believe that it is, I'm kind of just looking at it. So that allows you to do that. Now, how to find other probabilities. So what if I wanted the probability that x was greater than 2? Well, that's just going to be 1 minus the probability that x is less than or equal to 2. So I would take this and go 1 minus 0.76. So I would go 1 minus, and this, I could also go second answer. That pulls up the last answer. Makes it really easy. 0.2835. If I wanted greater than or equal to, say 2, then I have to do this a little bit differently. I have to go 1 minus the probability that x is less than or equal to 1, because I don't want to subtract off the 2, and this is and equal to 2, I would be subtracting that off. So I can go 1 minus, then I can go to my binomial, CDF. My number child is still 5, but now I want to change my x value to 1. And I've already done the 1 minus, so this whole thing is equal to 0.6276. Now, what if I want the probability that x is strictly less than 2? Well, then I just have to do the binomial probability that it's less than or equal to 1 less than that. Because if it's strictly less than 2, it's either 1 or 0. So I can do that. Pull this back up again. I don't want the 1 minus on here anymore. So let me take the 1 minus off of there. So this one ends up being 0.3724. So now let's say that I want to know the probability that 2 is less than x is less than, say, 4. Okay? Well, now what I want to do is I want to take the probability that it's less than or equal to 4, and I want to take off the probability that it's less than or equal to 1. Because I don't want to take out the probability that it's 2. I want to take out 0 and 1. So this is going to give me the probability that it's less than or equal to 4, 0, 1, 2, or 3. Then I want to take out 0 and 1 because I want to leave 2, 3, and 4 on there. So I'm going to go do this again. Whoops, B. Okay, I'm going to do this with 4. Paste. And this one is 0.9921 minus, I already know what that one is, 0.3724. So, go pick it up. And I end up with 0.6197. And that's my answer. So I can find any of the other probabilities just like this. So, using that information, let's talk a little bit about high-speed internet. In the US, 87% of individuals have access to high-speed internet. If 10 Americans are chosen at random, what is the probability that exactly 8 have access? So we're going to do this using binom PDF. N is 10. P is 0.87. And our number, our X or K, is 8. So we go do this, and we want to go, and you can also do this by just pulling alpha math. It pulls it up. So trials is 10.87. X value is 8. There we go. Enter, enter. 0.2496. What is the probability that at least half have access? So half would be 5. So the probability that X is 5 or more, greater than or equal to 5, is equal to, now remember how we do this, 1 minus the probability that it's less than or equal to 4. Because remember, we don't want to take off the 5. So we want 1 minus binom CDF. So we're going to go B, second apps. Oops. No, I did second. Oops. Alpha apps. Sorry. Whoops. Oh, goodness. 1 minus. There we go. Ugh. 1 minus, I keep forgetting to go to distributions. Second distributions, now I can go alpha B. And trials, again, 10.87 and 4. And I did the 1 minus already, so I have, ooh, that's a lot, 0.9994. What's the probability that less than 10 have access? That's the probability that X is less than 10. So that's the probability that X is less than or equal to 9, which is what? We're going to go binom alpha apps. So we're just going to go to 9 and paste. And we get 0.7516. Okay, less than all of them. 75% chance that less than 10 of them have it. 25% chance that everybody that you select at random has internet access. So what is the probability that between 7 and 9 of them? And I didn't write the word inclusive, but it's assumed. Because if it wasn't inclusive, it would just be 8. And that'd be the first question. So this is the probability that it's less than 9 minus the probability that it's less than or equal to 6, because we don't want to take off 7. So we're going to go distributions, B, oops, did it again. Distributions, there we go. I keep doing that. Okay, so 9's already in there, so we can pull this one. Now I'm not going to hit enter again. I'm actually just going to hit minus right now. And I'm going to go back to distributions. I hit second again, didn't I? Distributions. Not second, alpha, B, enter, minus, I'm going to be careful this time, alpha, apps, there we go. Now let's change that to 6, paste, now we have them both, and this is going to be equal to 0.7203. So what is the mean and the standard deviation for this random variable? Well, the mean is just 87% of 10, so 0.87 times 10, which is 8.7. So you're expecting about 8.7 of the people that you sample should have internet access. And alpha, or sigma rather, is a square root of 0.87 times 10 times 0.13. Let's see what that is. Oops. 0.87 times 10 times 0.13. And what do we get? 1.0606 3. And there you go. So that's your standard deviation.